Good evening, all. We are starting the last topic of this partial differential equation, section 7.8, non-homogeneous problem. I'll share the solution of the questions of this exercise. You can ask me if you come up with any doubt. All right. In this section, we consider the initial boundary value problem, which says that utt is equal to c square uxx. Till here we have done the solutions, right? Now there is some constant will be there or some variable part will also be there. There are two types of conditions where this h will be a constant and somewhere this h will be a function of x. Let's say this instead of x, let's take it as capital N. Again, x is lying in between 0 to L, where t is greater than 0. And the initial value conditions are that at t equals to 0, the value of u is small fx. I'll take here. X is lying in between 0 to L. Differentiation of u with respect to t is some gx. Again, x is lying in between 0 to L. And the boundary problems that at x equals to 0 it is a, and at x equals to L it is some b. And t is greater than equals to 0. Right? There is a solution that we'll consider, that the solution will be some in terms of xt, and along with that there will be some terms which consist of x only, because we have here this fx. So I consider this kind of solution as well. Let's see how we are going to solve it. Consider the solution of the form uxt. Here, be careful, where is this u and what is this v and another variable, another term which consists of x, only x. All right. This is v xt plus some ux. Here, this is the solution that I have considered. This is the term which consists of only variable x. And this, in the solution, this term is consisting of x and t. All right. Now see, let's consider this as first. Mark this as first, and let the solution that I have considered as second. If this is a solution, then it will satisfy the given equation utt. Utt will be what? vtt plus, ये सिर्फ x की term है, so it will become 0. c square uxx. How uxx will look? vxx plus capital uxx, because this is the term which consists of only x. So double differentiation of this will be here, plus fx as it is. So from first and second, utt will be what? vtt, because double differentiation of this with respect to t will make this 0, right? c square uxx. How uxx will look? vxx plus capital uxx plus fx as it is. All right. Now, if I say that this ux is also the solution of this equation first, if that capital ux I have taken in the solution is the solution of the given equation, then it must satisfy the first equation. Then how will it look? Capital U will satisfy this equation. Capital U with respect to t, I'm differentiating, it will become 0. T square, capital U with respect to x, double differentiation with respect to x will be there because ux is the function of x plus fx as it is, right? So it will become 0 is equals to c square uxx plus fx, right? So here I can say that capital uxx will be minus 1 upon c square fx, right? Nothing. All right. Now, how will the initial conditions will look? See here. Because I know that c square uxx plus fx has become 0, what will happen to this equation? Let's mark it as 3. Uxx is basically minus 1 upon c square fx. So if you put it over here, how will it look? See, mark it as from third and fourth. We get VTT equals to c square vxx, I'm opening the bracket, plus c square uxx plus fx, which is 0. VTT is equals to c square vxx. We have solved this equation already, right? But it is here in terms of v. So we get here this VTT equals to c square vxx, the equation that we have solved already, right? Now what will happen to the initial conditions? We look at the values which are given to you and we look for v. How does it look here? In this VTT equals to c square vxx. All right. Let's mark this as fifth. Then for fifth, I'll check the boundary conditions, the initial conditions which are given to you as well. X0 is given to you as fx, right? Let's check how u looks at t equals to 0. At t equals to 0, it will be what? Vx comma 0 plus ux. Ux will remain as such. Here in place of t, you will put 0. So from second, we have taken this. It will become what? V of x0 plus ux equals to fx. That means v at x0 will be fx minus ux, right? The first condition. The second was ut at x0 was gx. That means differentiation of u with respect to t. With respect to t, it will become 0. It will be vt. You differentiate v with respect to t. And you will put the value of t as 0. You will get this as gx. Again from the second equation. Alright. I'll mark it here. This factor and this factor. Alright. Now for the boundary conditions, it says u0 comma t is a when x is 0. When x is 0, it will be u0 and it is v0 comma t. Boundary conditions. u0 comma t is given to you as a. That means v0 comma t plus u0 will be a, right? And ul comma t is given to you as b. So it will look v l comma t plus u at l is equals to b. And we know if I want the boundary conditions to be homogeneous, we must have this V0t and this VLT as 0. If this V0t is 0 and VLT is 0, I need this U at 0 will be A and this U at L will be B. Because I need the boundary conditions to be homogeneous. So, for boundary conditions to be homogeneous, we must consider that at this initial point of U, the value is A, and at the end point, the value of U is B. If we put this over here, I will get what? That V at 0 comma t is 0, V L comma t is 0. So, by these conditions and these two conditions and this fifth equation, the new problem has become. Therefore, new problem has become VTT equals to C square VXX with Vx comma 0 is equals to Fx minus Ux. Vtx comma 0 as Gx and V0 comma t equals to 0 and VL comma t is equals to 0. This condition we have solved already. Or we'll assume separation of variables as a solution, and then we'll separate the variables and then we'll solve it stepwise, right? In first two cases, then lambda was 0 and lambda was greater than 0. The conditions were trivial, so our solution was trivial. And we'll take the third case when lambda was less than 0. In lambda less than 0, we get the solution of V, right? The same thing we are going to follow. I will tell you shortly how we are going to write it. All right. I'll take let V as X into T be the auxiliary solution. We have done that already, so I'm not doing it again. All right. Then I'll put it in the given equation, that was VTT is equals to C square VXX. VTT means X into T double dash equals to C square X double dash into T. Right? So it will be T double dash upon C square T is equals to X double dash upon X. Right? This is in terms of X, this will be in terms of T. Right? Because we have separated the variables, so we'll put it equals to some lambda, some constant, and we'll solve it separately. Right? So for X double dash upon X equals to lambda, the equation has become what? D square minus lambda of X equals to 0. That we are solving the part which we have solved earlier in the previous solutions. So I'm not doing it in detail. All right. So I'll take the first case. When lambda equals to 0, we have solved it already, the trivial solution. I'm not writing it out. You do it by yourself. Case 2, when lambda is greater than 0, right? Again, I'll get the trivial solution. All right, now I'll solve the third case when lambda is less than 0. Although it is also the same part, but let's solve the third part because it's a bit lengthy when lambda is less than 0. So we'll put lambda as some minus m square where m is positive, right? So the equation will become x double dash upon x equals to lambda. That means equals to minus m square. So it will be d square plus m square x equals to 0. So it will be basically what? D plus iota m into d minus iota m. And we know whenever we have got iotas, we get the solution in a cos mx plus b sin mx, right? Then we put the initial conditions that we'll do in these cases as well, right? X at 0 is 0 and x at L is also 0. According to the boundary conditions. X at 0 is equals to 0 and x at L is also 0. So at 0, I'll get a cos 0, which is 1, a as 0, and here I'll get a0, that means b sine ml equals to 0. If b is equals to 0, we get the trivial case. When b is non-zero, we get sine ml equals to 0. And this is only possible when the value of this ml is equals to some n pi. So we get the value of m as n pi upon L for L n belonging to natural numbers, right? So we get x value as b times sine mx, that means n pi x upon L, right? For all n belongs to natural numbers. And if I'll talk about the series, I'll get xn as bn for series. I'll get the value of xn as bn sine n pi x upon n, right? Now if I talk about t, similarly, t double dash t upon c square t is equals to lambda, right? Again, I'll take three cases. First two are same. Case 1, lambda equals to 0. Case 2, lambda is greater than 0. Case 3, lambda is less than 0. We have solved it already. I'm writing the solution here directly. Alright. So here for tt, we used to get c cos n pi c t upon L plus the d sine n pi c t upon L. Alright. Till here, I hope it is clear. Alright. Okay. Now for series, if I talk about, we will be Cn times cos n pi ct upon L plus d sine n pi ct upon L. When I merge these two x and t, I'll get the solution of v here. So vxt will be x into t, and I'm talking about normal here, vn will be this for series I'm talking about. If I talk about vxt, I'll get the summation of xi's and ti's for all n belonging to natural numbers, right? For n equals to 1 to infinity. So I'm merging this bn into cn as an and bn into dn as v, alright? Till now we have done it already, so I hope there is no confusion about this. An cos n pi ct upon L plus bn sine n pi ct upon L into this xi series, which was sine n pi x upon L, right? This was the solution that we have got for each of the wave equation, right? Now, I'll get the initial conditions. What were the initial conditions? Where Vx is 0 is given what? I think fx minus ux was there, no? There. This was the problem, right? So if I look at this initial condition, that Vx0 is fx minus ux and Vt0 is gx. With the initial conditions, this will be fx minus ux, right? At t goes to 0. This will be 1. This will become what? 0. Right? So I'll get summation an sine n pi x upon L equals to fx minus ux. And I know this has become the Fourier series. So with how an will look as 2 upon L from 0 to L, here the function is this. So I'll write it over here in the integration fx minus ux into sine pi on dx. Right? And the second condition was given to you Vt at x comma 0 as gx. Vt at x comma t. We have done this, right? Vt at x comma t. Vt, I have to differentiate this with respect to t. It will become an sin n pi ct upon L into n pi c upon L plus bn cos n pi ct upon L. And then I substitute t as 0. I'll get this bn into 1 into n pi c upon L. Write it down. I'm writing it directly. Summation bn sin n pi x upon L. That's right. So n pi c upon L into sin n pi x upon L equals to gx. Where how bn will look 2 upon L into this n pi c upon L, right? So here it will come L into n pi c. Because I have to write this n pi c upon L here as well now with bn. So I transpose it to the other side. All right. 0 to L gx into sin n pi x upon L. Cancel this out, this L. It will become 2 upon n pi c. All right. Now moving forward, I have got the solution of this Vxt. This Vxt I have got. And I have got this for this problem, right? Now, I have solved this for Vxt. What will happen to the capital Ux that I have taken here? This capital U. That I know the double differentiation of this capital U is this, right? So from here, I can find out the value of this capital U, right? So I'll solve this fourth question now, fourth equation. Now, from equation 4, I have this capital Ux6 as 1 upon c square fx with negative sign. So I have to find capital U here, so I'll integrate it twice with respect to x. So first integrate it with respect to x. I'll get ux as minus 1 upon c square. I know I'm integrating it with respect to x, so the limit will be from 0 to x. I know that this is function of x, so I write some other variable with this plus some constant, right? So let's say this as C. Now again integrate with respect to x, you will get u as minus 1 upon c square here. Again, I have to integrate it, right? So what I'll do, I'll take another variable, say 0 to, I'll take another variable, say eta. The final limit is from 0 to x, and here I am integrating it from 0 to eta, where this f of xi dxi is as such, which when you integrate, then you integrate it with respect to eta. Plus c, I'm integrating with respect to x, so I'll get x and some another constant d. This is very important to reach till here, right? Now I have to find the value of this capital C and capital D. For that, I'll use the initial conditions that I know. I've taken the boundary conditions homogeneous. So u at 0 was A and u at L was B, if you remember. To be homogeneous, I have taken the boundary conditions that at end points, the value of u is A and B. And through which we will get the values of C and D, the constants here, right? Since u at 0 is A, when x is 0, this integration part will become 0, C into 0 will be 0. So I'll get the value of D as A, right? Now u at L is B. Let's find out. Minus 1 upon C square, 0 to L, 0 to eta, some xi with respect to xi, then I'll integrate with respect to eta, the C into L plus dt, which is A, right? Let's find the value of C from here. Equals to 3. So what I'll get, I have to find the value of the C, right? So will be what? B minus A, C into L, right? Plus 1 upon C square, 0 to L, 0 to eta, F, dz eta, right? When I transpose this L to the other side, it will become B minus C upon L and 1 upon C square into L, right? That's it. Just put the values of D and C in the given U. That's it. We've got the solution. We've got V as well as V. So I'll get UX. We get UX as minus 1 upon C square, 0 to L, 0 to eta, F xi d eta plus this value C into X. We can say B minus A upon L of X plus X upon LC square of this integration, right? Plus D. D is A. That's it. All right. This is our solution. Now we'll consider the second case, B part, where we consider the problem where the non-homogeneous term is some constant h, not in terms of x. The problem has utt equals to c square uxx plus some h, where h is a constant. With the initial condition given at t equals to 0 is 0, ut at x0 is 0, the boundary conditions at x equals to 0 is 0. And at L, it is also 0. Alright. Let's take this whole as 1. Again, I'll consider the solution, just like the previous one. Consider the solution as uxt as some v plus some say ux. I'll take the same function, same solution that I have taken already. Alright. So what will happen here to the equation utt? It will become what? vtt equals to c square plus from first and second we get utt is what? vtt, because ux will become 0. Equals to c square, uxx will be vxx plus uxx plus h. Right? अब हमारे पास क्या है? Conditions. Again, if I'll take ux to be the solution of this first equation, utt will become 0 equals to c square capital uxx plus h. The same thing that we have done already. If this ux, this capital ux is the solution of the given equation, will satisfy it, then utt will become 0. 0 equals to c square uxx plus h, right? With u at 0 will be what? A और B यहाँ पे 0 0 है. So I'll get u at 0 is 0 and u at the end point as 0. Previously there was u at 0 was capital A and u at L was capital B, which is not here, right? That means capital ux आ गया आपका minus h upon c square. देखते हैं इसको सॉल्व करेंगे अभी आते हैं वेव इक्वेशन पे. ये जो हमारी बनेगी यहाँ पे, इसको हमने सॉल्व किया, ओपन किया ब्रैकेट सी स्क्वायर वी एक्स एक्स प्लस सी स्क्वायर यू एक्स एक्स प्लस एच. सी स्क्वायर यू एक्स एक्स प्लस एच इक्वल टू 0 है. मार्क इट एज थर्ड. So from third VTT, from third we get VTT is equals to c square vxx plus c square vxx plus h equals to 0 from here, right? So here's the condition आ गई with initial conditions v at x comma 0. v x comma 0 कैसे हो जाएगा? ux comma 0 which is 0 plus ux, यानी कि अगर यहाँ से वी एक्स कॉमा 0 की वैल्यू निकालते हो, ये तो 0 हो गया, ux इधर जाएगा तो माइनस ux हो गया. So v at t equals to 0 is minus ux and vt at x comma 0. अब vt निकालो पहले तो. vt कैसा दिखेगा? यहाँ से vt is ut, ux तो ये 0 हो जाएगा, x की टर्म है. ut is what? 0. So vt will become 0. अब बाउंड्री कंडीशंस कैसे दिखेंगी? 0 कॉमा टी और एल कॉमा टी पे. 0 कॉमा टी पे u भी 0 है, u एट 0 भी 0 है, कैपिटल u एट l भी 0 है, u एल कॉमा टी भी 0 है. तो दोनों एंड पॉइंट्स पे v की वैल्यू आ गई 0. दिस इज आवर प्रॉब्लम. ये हमारी प्रॉब्लम हो गई थ्रू आउट, राइट? इसको हमने ऑलरेडी सॉल्व किया हुआ है, ठीक है, पीछे. सो लेट्स लुक एट दिस कंडीशन. मार्क इट एज फोर्थ. Mark it as fifth. From fourth, we know this capital UXX is minus h upon c square, right? this minus h upon c square. When I integrate it, I'll get ux as minus h upon c square x plus p. When I integrate it again, it will become qx equals to minus h upon c square x square upon 2 plus p times x plus q. Integrate it with respect to x. Again, I have integrated with respect to x, right? I have to find this capital P and capital Q. I know the boundary conditions u0 is 0 and ul is 0. U at 0 is 0. When x is 0, that means q is 0. If I put it over here, and u at l is 0. That means minus h l square upon 2c square plus pl plus q. Q is 0 already, right? So equals to 0 again. L common ले लो. Minus h l upon 2c square plus p equals to 0. L तो हमारा 0 हो नहीं सकता because L is the end point. So I'll get P as HL upon 2c square. It cannot be 0, right? Okay, so if I substitute here, what I'll get capital U as? Ux is minus h upon c square x square plus px, yani plus hl upon 2c square x. So if I take common here, ux will be h upon 2c square. I can take x as common, L minus x. Right, I've taken this term first. All right. Let's see. We have solved this part already here. Right, VTT is equals to c square vxx. हमारे पास आया था ext is summation an cos n pi ct upon L plus bn sin n pi ct upon L into sin n pi x upon L. I know here this gx is 0. And when this gx is 0, that means bn part will not be here, right? So what will be the solution of the fifth equation? Solution of equation 5. Mark it here. Let's say this as 6. Right. The solution of equation 5, because gx is 0, that a and bn parts में से bn will be 0. So I'll get vxt as summation an cos n pi ct upon L into sin n pi upon L. Alright. And how will this an will look like? Here this is fx. Fx is what? Minus of ux. Right? So where an is, we know, 2 to L, from 0 to L, fx sin n pi x upon L इस तरीके का होता था. fx क्या है यहाँ पे? माइनस ऑफ कैपिटल ux. u की वैल्यू अभी निकाली है यहाँ पे. दिस पुट कर दो. माइनस ऑफ ux from which equation this fx has come minus ux. Name that equation. This fifth equation. fx की जगह है minus ux. gx तो 0 था ही. gx 0 we have used. Now from equation 5 I have found out this minus ux. Minus I've taken outside. U, capital U is what? H upon 2c square h upon 2c square x L minus x into sin n pi x upon L dx. I get Vxt as minus 2 upon L, 0 to L. Take this h upon 2c square outside. 2 will get cancelled out. L e square. When I open the bracket, it will become Lx sine n pi x upon L minus x square sine n pi x upon L dx. So open the brackets, minus h upon L c square 0 to L Lx sine n pi x upon L plus h upon L c square 0 to L x square sine n pi x dx. So dx. You will solve this part by using what? Isolate. Take this L outside. Again, this part you will solve by isolate, right? What matters over here is what will be the form of n. If n is odd or if n is even. If n is odd, you will be able to integrate it. What if n is even? If n is even, say 2, 4, 6, that means it is coming as 2 times 2 pi something. 2 pi multiplied by anything will be even number. And 2 pi, at 2 pi, signs are always 0. So, I'll get this a and we're solving now. I'll get this. An. So the cases that have become here is that an will be 0 when n will be even. What will happen when n is odd? For n to be odd, that means sin n pi x upon L will exist. And that I have to check by solving it via isolate. Do one thing, try this. X, take this x as 1 and sin n pi x upon L as second. Here x square as 1 and sin n pi x upon L as second. By solving it and putting the limits 0 to L, you must get over here is 4L square h upon pi cube n cube c square with negative sign. Check. अगर ये नहीं आता है तो हम डिस्कस करते हैं, अदरवाइज ये इजी है, आइलेट से सॉल्व करोगे आंसर आ जाएगा. ठीक है, कुछ वैल्यूज हैं, जब 0 पुट करोगे 0 हो जाएगी, L पुट करोगे तो 0 हो जाएगी, cos n पाइज आएंगे, sin n पाइज अपॉन L रहेगा, जहाँ पे L पुट करोगे n पाइज हो जाएंगे sin n पाइज में, वो कैंसिल हो जाएगा. सॉल्व करना इसको इजी है, ये आना चाहिए. यू हैव टू शो इट. दैट्स इट. यानी n ऑड है तो हमारे पास an इस टाइप का एग्जिस्ट कर गया. an की वैल्यू ये आते ही यू विल पुट इट ओवर हियर. So what you will get? Vxt as, we get Vxt as summation 4L square h upon pi cube n cube c square with negative sign. An will be this, cos n pi ct upon L sin n pi x upon L. Cos n pi ct upon L sin n pi x upon L. But here is a twist, that n must be odd here, right? So instead of putting here n equals to 1, 3, 5, for solving here from n equals to 1 to infinity, what I'll do, I'll put it over here instead of n as odd. And how will the value of n I will write so that it will become odd automatically if I will write in place of n as 1, 2, or 3. For odd functions, it is of the form 2n minus 1. So what I'll do, I'll replace this n with 2n minus 1s. So it will become minus 4l square h upon pi cube 2n minus 1 whole cube c square cos 2n minus 1 pi ct upon l sine 2n minus 1 pi x upon l. Alright. This is Vx only. Plus Ux was the solution for this equation, this Uxt. From second and sixth, we get, therefore, from second and sixth equation, I get Uxt as Vxt plus capital Ux. Capital Ux was Hx upon 2c square L minus x. Hx upon 2c square into L minus x. Vxt is this. So you can replace this Vxt here with the above equation with this. Alright, and start. I'll show you some solutions of this exercise. If you come up with any doubt while solving the problems, you can ask. Alright, so here your theoretical part is finished. All the exercises part which you have to try and practice. It's up to you. As much you practice these questions, you'll get a hand-on on how to integrate these typical problems. So all the best with you.